Welcome to AP Chemistry at Haneke High School. I'm Brian Brown, and today we'll be starting the first of two chapters in a two-part series dealing with bonding, bonding theory, and molecular geometries. Now, Chapter 8, along with Chapter 9, comprises about 9 of the 75 multiple choice questions, and it appears on the FRQ section every year. So you can assume this will be important material for the AP test. Now, if only noble gases are stable as atoms, how do other atoms achieve stability? Well, they do it through chemical bonding. Now, there's three basic types of bond. The ionic bond, if you remember this from last year, that's an electrostatic, which means positive to negative attraction between ions, so Coulomb's law situation. And it's typically between metals and nonmetals, two substances that are very different in um, ionization energies, and they create very, very strong bonds between them. The next type would be covalent bonding, and covalent bonding is a sharing of electrons, and you typically see this between two nonmetal substances. When one substance isn't strong enough in electronegativity to steal the electron from the other, they end up sharing electrons. And the third type of bonding we'll end up looking at in the chapter is metallic bonding. Now, metallic bonding is a type of bonding that explains why metallic substances and alloys can end up becoming stable. And it's metal atoms bonded to several other atoms. And it's usually metal to metal bonding that we're looking at here. Now, all chemical bonds form because the electron to proton attraction lowers the potentiality of the system as the bond gets formed. In other words, as they come together, they create a more stable, lower potential energy situation than when they were apart. So everything occurs about stability and potential energy. Remember, lower energy, more stable. The distance between the bonded particles is a balance between the attractions of the oppositely charged particles and the repulsions of the like charged particles. This should sound very familiar because this is a core theme. We've hit this again and again and again in the last few chapters. So when you take a look at the situation, as we have two, in this case, hydrogen atoms, as they're far apart, so at time one over here, the substances are very far apart. So we're starting over here in this diagram. There's really very little attraction between the two particles because they're so far apart. But as they move together, there starts to form an attraction between the nucleus of one atom and the electrons in the other atom, and the potential energy of the system starts to drop. And the particles then move closer and closer together and become more and more stable. And what happens is they reach a distance right in here, and that distance is really the perfect balance between our attractions and our repulsions. If we try and move the particles any closer together, what ends up happening is the repulsions between the electrons between the two atoms and the nucleuses between the two atoms starts to increase the potential energy, which makes a less stable situation. So our bond length is really formed here when we reach that perfect distance between the balance between the two, where we've maximized attractions to minimize repulsions, and we end up forming a chemical bond. So at this point, we've formed a chemical bond. Now the difference between here and here depends on really the direction you're looking at. This would be the energy released when the bond gets formed in the first place as a more stable, lower potential energy situation. This difference in potential energy would be released versus if you're trying to break the bond. So this would be the energy that gets absorbed by the molecular system when you're attempting to break the bond. Now, the electrons involved in bonding are called valence electrons. Now, valence electrons are found in the incomplete outermost shell of an atom. Now, a visual method for showing valence electrons, this is something you got into at pre-AP chemistry at the end of our electron configuration. We just haven't gotten that far yet, so we're introducing it here. So a visual method for showing electrons in a valence level is to use dots around the symbol for the element. The number of valence electrons for bonding is indicated by dots. So these symbols are called Lewis symbols or Lewis electron dot symbols. So usually we call them Lewis electron dots. And you can see in the far column over here that if you had one valence electron, like in the case of lithium, you would put one dot. If you have beryllium, two valence electrons, two dots, and so on. And while there is a notation for exactly where these dots should go, the general rule of thumb is no more than two dots on a side and just space the dots out and you'll be fine. Now, atoms tend to gain or lose or share electrons until they are surrounded by 8 valence electrons. This is known as the octet rule, something you should remember from last year in pre-AP chemistry. Now, an octet consists of a full S and P subshell. Now, we know that S2P6 is a noble gas configuration, with the exception of helium. So for hydrogen and helium, their full outer shell would be just a full S. So S2 would be the equivalent of an S2P6 for the rest of our noble gases. Now, we assume that an atom is stable when it's surrounded by 8 electrons, 4 electron pairs. Now, elements 1, 2, 5 are too small to form full octets. And if you think about it, it makes sense why. When we have these very, very small substances, the electrons are close together. If we try and cram more electrons in there to get a full octet, we're going to have very, very large electron-electron repulsion. And the energy advantage we get by adding those valence electrons is less than the disadvantage caused by having that great electron-electron repulsion. So elements 1 through 5 are really too small to form full octets. Now, some larger non-metallic, which would be period 3 and greater atoms, can expand their valence shell to include 10 or even 12 electrons. These are expanded octets. You may remember these a little bit from last year. But for most substances, a full octet is going to be 8 valence electrons. There are a few, like hydrogen and helium, that's only 2. And there are a few that end up having expanded octets. They can be stable with more than 8. But for most substances, it's 8. That's why we call it the octet rule. But really, the octet rule refers to a stable outer valence electron configuration. Now, in forming ionic bonds, like when NaCl is formed from sodium and chlorine, chlorine removes an electron from the sodium and an ionic bond results. So your sodium ion, which has a very low ionization energy, so it's relatively easy to remove that electron, comes together with your chlorine ion. And you remember your chlorine ion, its electron affinity, very exothermic. So that energy that is spent to pull is more than made up for the energy that is released when chlorine absorbs that electron, and you end up with a lower potential energy, more stable situation with Na plus and Cl minus. They're oppositely charged, they attract, and you end up with what's called an ionic bond. So this is an electrostatic, an attraction between two oppositely charged particles to make a more stable, lower potential energy situation. Now, another way to show this reaction would be to use Lewis electron dot symbols as follows. So you've got Na with its 1 dot, Cl with its 7 dots, and that one electron from sodium will leave and go to the chlorine to form the situation that we see here. So now chlorine has a full 8 octet. Sodium lost that one on the outside, and now its new outer energy level would be the same as neon, which has a full octet, and it also becomes stable. We have two stable substances electronically, and they're oppositely charged. They attract each other. So the bracket around the chloride really emphasizes that all 8 electrons are located around the chloride ion. So they're localized around the chloride, and therefore it has a -1 charge. Now, the energy is dealing with ionic bonding. As we saw in the last chapter, it takes 495 kilojoules of energy to remove electrons from sodium. Remember, this is right out of our ionization energy table. So for a mole of sodium atoms, it would take 495 kilojoules to remove electrons from sodium. Now also remember from our electron affinity table, we get 349 kilojoules per mole back by giving the electron to chlorine. So does this mean that the formation of the reaction, um, the formation reaction is going to be endothermic? When we compare these two numbers, it looks like overall it's a positive 146 kilojoules. It's an endothermic situation. Well, it doesn't really explain, however. So on the surface, it would look by the reasoning, if we look at ionization energy, how much energy do we have to spend to remove the electron versus electron affinity, how much energy do we get out when we put that electron in. When we only look at those two situations, it looks like this should be endothermic. It should require energy for this reaction to happen. But when you actually see the reaction between sodium and chlorine gas, so we've got chlorine gas in the first graduated cylinder here, we introduce some sodium to that, some molten sodium, and a lot of energy gets released, a lot of light's coming off, and this white solid starts to slowly disperse and fall to the bottom of the container inside here as we make sodium chloride. So on the surface, it looked like it should be endothermic, but when we do the reaction, it's clearly very, very exothermic. So that means there's got to be a third piece to the puzzle if we're going to look at the energies involved in bonding here. So what is as of yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and chloride anion. So what's happening is we've only accounted for the electron transfer. We haven't accounted for the fact that as these two positively charged particles move close together, there is a attraction between the two, which creates a lower potential energy, more stable situation. So we've accounted for two of the three parts. If we really want to see why it's so exothermic, as those two positively charged and negatively charged particles come close together, they attract, and as you saw in that graph when I looked at the two hydrogen atoms coming together, a tremendous amount of energy was released when you make that more stable situation due to the electrostatic attractions that are created. So that's really what accounts for the third piece of the puzzle. It's the missing energy, and we call that energy the lattice energy. The energy required to completely separate a mole of a solid ionic compound into its gaseous ions. Now, this is actually the exact opposite of what we're looking at. So from our point of view, it would also be the energy that would get released when it gets formed. So it's really a measure of the strength of the electrostatic attractions that is the principal cause of ionic compound stability. So yes, ionization energy, electron affinity are a part of the equation, but they're really only a small part of the equation. The biggest piece of the puzzle is the lattice energy component. The energy associated with electrostatic attractions is governed by Coulomb's law. This is a law we've looked at in several different chapters. This is a core idea we mentioned last chapter when we talked about the farther you get away from the nucleus, the weaker your attractions, distance kill attractive force. That's Coulomb's law. Distance is on the bottom and it's a squared relationship. That's why distance has such a huge effect on electrostatic attractions. So lattice energy then increases with the charge on ions. So if you take a look at our two ions that are listed here, Q1 and Q2, the greater the charge differences between those two things, the greater the energy is going to be. So by Coulomb's equation, lattice energy is going to increase them with the charge. If you take a look at some common ionic compounds here and their lattice energies, you can see that. LiNF, a +1 -1 situation. 2,326. LICL, same thing, 2,127. But when we start to go to think, or oops, I'm sorry, I'm saying that wrong. When we look at LIF, it's only 1,030. Looks like I have to pause the tape here because there is somebody at the door. So there's two main parts to Coulomb's law. We have the Q component, which is on top, and that represents the charges of the ions that are attracting and repelling each other, and D, which would represent the distance between the two particles. Now remember, D, which is the distance between, is a squared, and it's an inverse. It's on the bottom. So as distance increases, it dramatically decreases the energy. And on the flip side, when Q increases, it increases the energy. So when you take a look at the table here, you can see with something like LIF, its lattice energy is only 1,030. It's a +1 -1. Everything in this row is a list of +1 -1s. They're all relatively small lattice energies. But when we go to a +2 -1 situation, you'll notice the lattice energies have increased. When we go to a +2 -2, once again, the lattice energies have increased. So lattice energies are related through Coulomb's law because really what we're talking about is an attraction between cations and anions, two oppositely charged particles, and that's exactly what Coulomb's law deals with. So lattice energy then increases with the charge on the ions. It also increases with decreasing size of ions, and here's a relationship to what we talked about back in chapter 7. So because the distance is a squared relationship on the bottom, it can have a big impact on the overall lattice energy. So if you remember from last chapter, as you go down a family, like here's a family, lithium, fluorine, chlorine, iodine, and fluorine. So we have Let's look at those first three, F, Cl, and I. Notice what's happening to lattice energy. Lithium is all the same size, but fluorine is significantly smaller than chlorine, which is significantly smaller than iodide is. And notice, as the ion gets larger in the case of I minus, its lattice energy was decreasing. So as the ion size decreases, and it decreases across a period, and it decreases or increases down a family, um, as it decreases, then the lattice energy is going to increase. So you'll notice that LiF, with that smaller fluoride, is a higher lattice energy than LiI. And you'll see the same thing, not just within a family, but you'll see the same trend within a group as well. It's just that it's going to be opposite because remember when you go down, you're getting a larger ion, so therefore you would see the lattice energy decrease, like in the case of going to I minus. Now, by accounting for all three of the energies that we're talking about, so if you look at ionization energy, electron affinity, and lattice energy, then you finally get a good look at the energy involved in a reaction like mixing sodium ions with chloride ions to make the compound sodium chloride. Now, this idea is known as a Born-Haber cycle because these were two scientists studying it. And honestly, you don't really need to be able to understand perfectly exactly what's happening. You just need to understand here that by looking at and all of the different reactions that are occurring and remembering that Hess's law says the sum of the individual steps equals the total, we can actually determine lattice energies then from a variety of other sources. So we have a number of different things that are happening through the course of this reaction. We have ionizations, we have electron affinities. Over here we have formations of several different things. So when we look at this overall energy, if we start with these, it's going to take some energy to form our sodium gas. It's going to take some energy to break apart our Cl2. Then it's going to take some energy to ionize our sodium. We can account for all those by looking at formations and ionizations. And then we also have energy coming back due to our electron affinity. And then the only other thing we have here is the formation of the sodium chloride. So that's another energy we can account for. So looking at the sodium solid reacting with the chlorine gas to make the sodium chloride solid, we can use formation enthalpies to determine that. So basically, we know all of the energies of all these steps, except for this one right here. And Born-Haber came up with a way to actually measure lattice energies using ionizations and electron affinities and formation reactions. And this general idea works with pretty much any formation of any ionic compound. If we account for all the formations and changes that occur in our atoms involved and their ionizations and their electron affinities, we can set up this cycle in which we're going to know everything except for the lattice energy. And we can use that in Hess's law then really to determine what our lattice energy is. So fundamentally what we're doing here is if we know the energy to do this, and we add to it the energy to do that, and the energy to do that, and the energy to do that, and then subtract out our electron affinity, then we can determine what our lattice energy is. And this is how lattice energy is determined for substances. So Born-Haber process is a way to look at the energies involved in all the individual steps here. And the key is it's a cycle. So we're starting right here, in essence, with our elements in their elemental state. And from there, we're accounting for all the energies involved in this whole process. Ionizations, electron affinities, other formations, both that are releasing energy and needing energy, and we can use all of those to determine what our lattice energy is. So if you really look at what's happening here, number one, so just to make the process a little easier to understand, so what we're going to do is review what I just briefly talked about. Number one, that's our heat of vaporization. So we're looking at how much energy it takes to vaporize the sodium solid into sodium gas. We can calculate that delta H. Two, we're looking at the decomposition of our chlorine atom. So you can look at it, the formation of the chlorine atom in its gaseous state here. 3, we're looking at the ionization energy. And remember what we're ionizing here is the uh, sodium ion. So we're moving electron from sodium. And then we're looking at the electron affinity caused when chlorine gains that electron. And then the 5th step here, that's really our target typically in a Born-Haber process. That'd be our lattice energy of our substance. Now, if we could look up that lattice energy, we would then know really the energies involved in all the first 5, and we could use those to calculate potentially the 6. So technically, if we know any 5 of the 6, we can calculate the last one. So let's say our goal was to calculate the formation enthalpy of sodium chloride. Well, if we know 1, 2, 3, 4, and 5, then we can figure out what 6 is in a Hess's law type situation. So that's really how we deal with and use lattice energies. It's one way to determine the formation enthalpy of sodium chloride from its constituent elements. Or, like I said, we could, if we look up the formation enthalpy and we knew everything with the lattice energy, we could use it to determine what the lattice energy is. So in this particular case, if you're looking at this from an energy standpoint, 4 plus 5 is going to be opposite in energy. So notice I've got 4 and 5 here in brackets, and I'm multiplying it by -1. It's going to be opposite in energy to the sum of the other energies. And in this case, because E6, it's going in the wrong direction. We're not adding energy, we're looking at a release of energy. Notice it's the negative here. So what we're really saying is if we add up this plus this plus this plus that, that's going to equal the opposite of the other two. And that's really what Born-Haber process is all about. It's studying the relationship of lattice energies to the other energies involved in the situation here. Now, these phenomena also help us explain the concept of octet rule. So metals, for instance, tend to stop losing electrons once they attain a noble gas configuration because the energy would be expended that really can't be overcome by lattice energies. So if we're going to spend some energy to go through one more ionization, then that really throws off the energy cycle too much, and we don't get back enough energy through the formation with our lattice energy to account for it. So we end up stopping at that ionization. So the ionization doesn't continue. So octet rule is really tied to this whole concept of, so why is it when we get that large jump in ionization energy, we don't end up losing any more electrons? Well, when you look at it from the actual processes, because you don't form an ion in a vacuum, that electron has to go somewhere else, so it's typically going to some other non-metal. When you look at any of those situations, you'll always see why it is going to stop when it reaches a certain um, ionization stage because it's just too cost prohibitive and there's not enough energy that's coming back through our lattice energy to overcome that huge increase that another ionization would cause. So really, phenomenon of octet rule are related to the discussion we've just had. And that ends our notes.